Hello everyone, what's up? Today I want to solve with you a pretty interesting problem about related rates. Now let's imagine this specific scenario. I'm going to say that we have a road over here, which is going to be something like this, okay? This is going to be a road. And I'm going to say that 30 feet away from this road, we're going to have some cops, just sitting around and seeing if they can catch anyone speeding, okay? This is going to be cops. Now in this road, well, we're gonna have cars, and we're gonna assume that you're sitting in your car and you're driving and you're probably going too fast. And the question that I want to solve with this problem is, are you speeding? Okay, I want to see, we want to see if your car is going too fast and the cops using a radar will detect that you're going too fast. So let's set some more conditions or numbers in this diagram so we can create a more complete situation. So now we have that the cops are 30 feet away from this road. Now we're gonna say that this portion of the road is going to be 40 feet long, okay? And now we can say that the cops, well, they have some sort of radar. I'm gonna say, these are like waves. So they have like some sort of radar. And let's say that, you're here in your car, okay? You're here, and well, you're probably going too fast. I'm gonna say that you're probably going at a speed of, I'm gonna say that your velocity, this is gonna be v, is gonna be let's just say 80 feet per second, okay? 80 feet per second, and let's say that this road has a speed limit of probably 95, okay? 95 feet per second, okay? Now, if we have this rate, this is gonna be a rate, so we can interpret it as a derivative. Mathematically, we can use it as a derivative. With this information, we can now figure out if the cops will detect on their radar that you're speeding, okay? So now, to solve this type of problem, the first thing that we want to do is, well, we want to assign some variables, okay? And that is, well, we want to use letters to represent magnitudes. So now, in related rates problems, you do not want to assign letters to measurements that will not change. So in this case, we know that you're moving and you're going in that direction. So we know that this 40 feet, that would be a measurement that will change, okay? Because this is your distance from this point over here to you, okay? This is a distance that will decrease. But 30 feet will not decrease because we're assuming that the cops, they're just sitting there, okay? So 30 feet will not move. This distance will not change. So we're not gonna give it any name or letter. 40 feet, well, we're gonna say this is gonna be x, okay? And the other measurement that we know will change is gonna be the hypotenuse of this triangle-like diagram that we have in here. Okay, we know this distance, the distance from you and the cop's radar. We know that's gonna change. Okay, and I'm gonna call that let's call that h. Okay, so let's say that it's h. Now, since this is a right triangle, well, we know we can use the Pythagorean theorem to relate all the information that we have in this diagram. So we know that x squared plus, now here comes, the math part of this problem. So every single time you're solving a related rates problem, you're going to write the equation and you're not going to differentiate just yet, okay? So you want to first write the equation and see, we can write the equation like this. So I'm actually gonna do like this. So I'm going to say this is going to be y. I know I said we should not give it a letter, but I just want to show you something that you can do. We know we can relate these three sides by saying y squared plus x squared is going to be equal to h squared, okay? Now, you could do something, and that is you could differentiate this equation using implicit differentiation with respect to time, okay? And you would get something like this. So you know the derivative of x squared is going to be 2x times the derivative of x as a function of time. We know that is going to be dx over dt plus 2y times dy dt. Okay, this is just implicit differentiation. And we know this would also be 2h times dh dt. Okay, so now this would be the equation that you get. Now, instead of writing y in the first equation, something you can do is you could also write the same equation, but replacing y with 30 feet squared, okay? Because you can see that in this equation, we said that y will not change. And if we know that y, the measurement y will not change, then dy over dt will be equal to 0, okay? And if this is equal to 0, this term in the middle will disappear, okay? So we don't really have to deal with it. We don't really have to deal with it anyway, okay? So you can just simply instead of writing y here, you can just say that, well, there's gonna be a constant that will represent y, and that is gonna be 30 feet squared, okay? And this will be equal to h squared. Now, when you do this, when you write this equation, you can differentiate it, and instead of writing 2y dy dt, you can just simply take the derivative of 30 squared, and you know that it's going to be constant, so that derivative equals 0, okay? So that's, I think this is, just an important notion. When there is a measurement that will not change, its derivative will be equal to 0. And therefore, it's going to be multiplying something, so that something will disappear, okay? Because it's just going to give you 0. So instead of writing this equation, well, you can write it with the constant already in, and you will just get the same thing, okay? So now, let's continue from this equation. So we know if we differentiate this, we will get this term over here, and this term over here. And 30 squared, that's going to be constant. So we just simply, at the end of the day, we just get these two things. Now, we can see that, well, these two terms, they have a factor of 2. So you can cancel out that factor. So you would get the following. You would get x times dx dt. And this is going to be equal to h times dh dt, okay? Now this is the equation that we have. Now, once you have already differentiated, the next step is plugging in values, okay? Now we know how much x is going to be. We know x will be equal to 40 feet because we really want to figure out in this moment of time. Remember, this is going to be a system that evolves with time. You're going to be moving, and that means that x will be continuously changing, but we only care about the instant. We only care about the instant where x equals 40 feet, okay? So when you're 40 feet away from this perpendicular point to the cups. So now we know x is going to be 40, and we know that if we want to find h, well, we would need to figure out what's the value of the hypotenuse in this right triangle right here. Now you can see that very conveniently I picked 40 feet because we would get a Pythagorean triple, just scaled by a factor of 10. So remember, there's a type of triangle that basically goes, you have something like this, and you have 3, 4, 5, and you could say you have factors of these numbers, so you have 3n, 4n, and 5n. This is the exact same triangle that we have in here. 5 would be the hypotenuse, and n is simply equal to 10, okay? So 5n, that would be 50. So we know h is equal to 50. So let me write this here. We know h would be equal to 50, and this would be 50 feet, okay? Now we can plug the value for x. So we know we have, I'm going to continue in here. We have 40 times dx dt. Now dx dt, I hope that you have already, you have already thought that if we want to see if we're speeding, well, we care about the horizontal speed, or we care about how this measurement, this horizontal measurement, is changing, okay? Because the radar, at the end of the day, cares about how much distance or how much your position is changing in the horizontal axis, okay? So that means that what we want to find is dx over dt, okay? So this is going to be our unknown. Now we know we have 40 times the derivative of x, and now h, we know that it's going to be 50, okay? And we already know how much dh dt is. Remember, we said that your velocity as measured by the radar is going to be 80 feet per second, okay? And there is something very important that I missed here, and that is, well, you know that this radar will measure, this distance should have a negative sign here, okay? Because at the end of the day, well, this measurement will decrease because you're getting closer to the cups, okay? So this velocity is actually negative, okay? So we're going to use a negative sign here, and well, we're going to plug the value. We're going to say that this value is equal to dh dt, okay? So we have 50 times negative 80, okay? And now we can just simply solve for dx dt. And we're going to get that dx dt is going to be equal to, so now we can move 40 to the other side of the equation. Now 80 over 40, that is going to be 2. And we have a negative there, so we have negative 2. And negative 2 times 50 is going to be 50 times negative 2. Well, we know this is going to be minus 100, okay? And now, well, I didn't really use any units here, but you know that this minus 100 would be minus 100 feet per second, okay? Now we said that, well, this road has a speed limit of 95 feet per second, and that means that, well, indeed you are speeding, okay? Probably the signs here don't make much sense because, well, this number should be way less than 95 mathematically, but in the real world, well, the negative sign just means that you're going to the left, okay? This distance is decreasing, and really what you care about is the absolute value of the rate, okay, which is going to be 100, okay? And 100 is greater than 95. So in conclusion, you are speeding, okay? That was, the main, I would say, the main theme or the main, idea of this problem. And well, now we have an answer to that question. So yeah, that has been everything. I hope that you enjoyed this video. You learned something. I think a very important notion when solving our related rates problems is being able to understand this part over here. Many people they usually they write y in here instead of just plugging in a constant, and then they don't know what to do with dy over dt. That's a very common and I would say probably very silly mistake. Because, well, you know that this measurement will not change, okay? You're not missing any piece of information, or you're not, you're not missing any information because, well, you should already assume that if this is not changing, dy over dt equals 0, okay? So, well, this term will yield 0, and you might as well just simply plug the constant in right there, okay? So you just get, you just get 0 when you differentiate that. So yeah, that has been everything now. This notion, very important. And yeah, that has been it. So I hope that you enjoyed this video, you learned something, and see you in the following one. Bye.